In RAG pipeline development, the standard instinct for improving accuracy is to upgrade the embedding model to the latest state-of-the-art release. But benchmark data consistently shows that this swap is a game of diminishing returns. Moving from a baseline model to a high-performance alternative typically yields only a marginal 1 to 2% improvement in overall accuracy. This diagram illustrates the real performance ceiling. While the embedding upgrade on the left barely moves the needle, adjusting the document preprocessing and chunking heuristics on the right drives a 15 to 40% spike in retrieval precision. This discrepancy exists because a RAG pipeline operates as two distinct engines with completely competing demands, the vector database and the large language model. The retrieval engine requires pinpoint, highly granular microchunks to execute accurate vector matching and minimize noise. Conversely, the generative engine requires broad, macro-level chunks to maintain the structural context and narrative flow needed to answer complex questions. Chunking defines the physical architecture of a system's semantic understanding. These boundaries dictate whether these two engines collaborate effectively or collapse into total imprecision. Many engineers default to large 1,000-token chunks. The logic is to provide the LLM with maximum structural context to prevent hallucinations and maintain readability. This diagram shows the mathematical cost of that decision. When a long academic paper is divided into these massive segments, they enter an embedding phase governed by mean pooling. Mean pooling compresses thousands of individual tokens from a chunk into a single dense vector representation in a 3D space. This results in semantic averaging. If a large chunk covers 5 distinct topics, its final vector becomes a mathematical average, anchored equidistantly between them. When a user query enters targeting a specific detail, like robotic manipulation techniques, the query vector aims directly at the relevant subtopic cluster. Even though the answer is physically inside the text chunk, the query vector misses the chunk's averaged coordinate. There is a physical gap in the vector space between the specific query and the diluted average. The retriever then returns irrelevant chunks that simply happen to have a closer semantic center of mass, even if their actual content is less helpful. Optimizing for LLM context via large chunks guarantees this averaging effect. You might achieve document-level recall, but you lose token-level precision. To solve for precision, pipelines often pivot to microchunks, segments as small as 128 tokens. In the vector database, this works perfectly. The query vector easily locks onto the exact mathematical coordinates of the targeted microchunk. But at the generation layer, the system fails. The LLM receives this isolated fragment. They began the prototyping process again with the substituted component, running the routine daily. This is context stripping. Tiny chunks sever the dependencies between sentences, leaving the model with isolated pronouns and undefined subjects. Without the surrounding paragraphs, nobody can determine who they are or what routine is being run. The retrieved answer is practically useless. Semantic chunking algorithms, which split text wherever embedding similarity drops, are often hyped as the theoretical fix for this isolation. This histogram shows how that strategy collapses at scale. When applied to an academic corpus, semantic chunking fractured the documents into over 17,000 fragments, averaging only 43 tokens. Forcing an LLM to synthesize an answer from dozens of these 43-token fragments destroys narrative flow. In these scenarios, generation accuracy drops to roughly 54%. Small chunks and semantic splitting optimize for retrieval boundary curity, but they dismantle the coherent context required for generative accuracy. Standard RAG design is limited by a single assumption. The exact chunk retrieved from the database must be the exact text passed to the LLM. The solution is hierarchical retrieval, also known as a parent-child or small-to-big architecture. This two-tier architecture starts with highly granular child nodes. These 128-token chunks are embedded and optimized strictly for crisp vector matching without the risk of semantic averaging. Each of these microchunks is then linked to a broader parent node, a 1024-token section that contains the full structural and narrative context. When a query enters the system, it strikes the highly precise child node vector, triggering a retrieval hit. But the system is decoupled. It registers the hit on the child node, but it does not send that fragment to the language model. Instead, the system follows the mapped edge upward, retrieves the massive parent node, and passes that larger contextual block to the LLM context window. Benchmark data shows that this small-to-big retrieval improves quality with negligible overhead, increasing first query latency by only 0.17 seconds. Hierarchical architecture resolves the granularity paradox. It provides the vector database with the precision it requires, while ensuring the LLM receives the context it demands. This horizontal slider tracks the failure modes of flat RAG pipelines. Pushing too far left results in context stripping. Swinging too far right leads to semantic averaging. On a flat architecture, finding a perfect middle ground is mathematically impossible because the physics of vectors and language models are in direct opposition. Escaping this compromise requires decoupling the architecture entirely. Stop relying on embedding model upgrades to solve what is fundamentally a structural problem with data boundaries. Before allocating engineering budget to fine-tuning, re-rankers, or new embedding models, audit the system's chunking boundaries. In enterprise RAG, precision originates at the initial split, long before the data ever reaches the generation layer.